Chapter 3. In this chapter, we are going to talk about acids and bases. You remember them from general chemistry and a lot of equilibrium, constant, and pK values calculations for them. We are not going to work on calculations in this course. We just look at the role of acids and bases in reaction mechanisms here. First, we need to know what is an acid and what is a base. Most of the time, acids are sour if you taste them, such as lemon and vinegar. Bases are usually bitter and they feel slippery. A lot of laundry detergents and soaps, they are in the category of bases. In chemistry, we have a pH scale that tells us how acidic and basic something is. And the pH scale goes from 0 to 14. So pure water is neutral, so it has the pH of 7. Anything that is more acidic than water falls within the region of acidic compounds from 0 to 7, and anything that is more basic than water is in the basic region from 7 to 14. In organic chemistry, choosing the right acid and base is very important because they need to be strong enough to complete the chemical reaction. So pKa values are very important in organic chemistry. There are several definitions for acids and bases in chemistry. In this course, we are mainly focusing on Bronsted and Lowry definition. Based on their definition, an acid is a compound that donates proton. Proton is a hydrogen atom that lost an electron, that doesn't have an electron, and we show that as H+. So an acid is a compound that donates a proton, and a base is a compound that accepts the proton. If you look at this reaction, we have hydrochloric acid reacted with water to form chloride anion and hydronium ion. So hydrochloric acid gave its proton to water and formed the chloride anion. So it is the proton donor. It is an acid here. And base accepts the proton from the hydrochloric acid to form the hydronium ion. So it is a proton acceptor. It is our base here. Water is a base in this reaction. Two other definitions here, conjugate acid and conjugate base. So when the base accepts the proton, or what we say is becoming protonated, it will form conjugate acid in the other side of the equation. So protonation means accepting proton. And when the acid loses the proton or gets deprotonated, it will form conjugate base in the other side of the equation. So deprotonation means losing protons. If you look at this equation here, we have hydrochloric acid reacts with water, form chloride anion and hydronium ion. So hydrochloric acid gets deprotonated, loses the proton to form the chloride anion. So hydrochloric acid is our acid and forms the conjugate base in the other side of the equation. Water accepts the proton to form the hydronium ion. So water is our base and forms the conjugate acid in the other side of the equation. Now, as a practice, let's look at this reaction here, label acid and base and their conjugates in this equation. So, alkoxide anion reacts with water to form alcohol and hydroxide anion. So as you can see here, water gets deprotonated, loses the proton to form the hydroxide anion. So water here is our acid and forms the hydroxide anion, which is our conjugate base. So conjugate base and acid, they are similar species, they are just different in the number of protons that they have. And the alkoxide anion takes the proton and forms the alcohol. So alkoxide is our base and forms the conjugate acid. Again, the base and conjugate acid, they are similar species, they are just different in the number of protons that they have. Another thing that we need to talk about is reaction mechanisms. So anytime in this course that I talk about mechanisms, I mean electron pushing or flow of electron density from one place to another in a reaction. And if you remember, to show the movement of electrons, we use curved arrow. So this is our curved arrow. A curved arrow has a tail which shows where electrons are coming from, shows the source of electron, and it has a head that shows where electrons are going to, the destination of the electrons. So if you remember, we used a curved arrow while drawing resonance structures, but there is a big difference here. In resonance, we know that we cannot break a single bond, and those arrows were just helping us to draw all possible resonance structures for a single molecule, all the structures that can define only one molecule. But here in reactions, we are going to make different compounds. So we'll see that single bonds can also break to make a new bond. So we are dealing with breaking and making bonds. Now, if you look at this generic reaction, the base takes the proton from the acid. So our source of electrons are in the base, so we have the tail of the arrow on a base, and it goes to the proton. We know that proton is a hydrogen without electrons, so it lacks electrons. Therefore, the base can bind to the proton. And now we know that each bond has 2 electrons, so these electrons in this bond will move to the A atom. So again, the tail of the arrow is in the bond because we have electrons there to the next atom that can accept the electrons. So as you can see here, we are breaking a single bond in HA and form a single bond, make a new bond to form the BH molecule. So that movement of electrons is very important in organic chemistry. This is a major topic in this class, so you should be able to recognize where electrons are coming from in the reaction between 2 species and where they are going to, and show this movement by drawing curved arrows. Okay, this is the practice here. I want you to look at the starting material and the products and define where you need to draw the arrows to show the movement of electrons. Generally, when you want to draw the mechanisms for acid and base reactions, there are a few hints that can be helpful for you. So the first one is always base attacks the acid. So for example, if you look at here, this is our base at the very bottom of this page. So always base attacks the acid. Another important thing to remember is acid cannot lose its proton without base attacking it. So attacking of the base and losing of the proton is basically simultaneous. So it's happening at the same time. And we generally call this type of reactions a proton transfer, because basically we are transferring proton from one species to another species. Now, looking at the real reaction here, so let's define what's happening. We have an acid here, so we know that acid donates the proton. So this is the proton that we have, and base accepts the proton. So we know we have our base. Therefore, to show the movement of electrons, electrons are moving from the base to the protons in an acid. And now these bonding electrons right here, they moves to the next atom. So this is how we draw the electron transfer, the electron flowing in this mechanism. If you look at here, the base accepts the proton, forms water, our conjugate acid. An acid loses the proton to form this anion, our conjugate base. Once again, be very careful while drawing your arrows in mechanism. The arrow has to be started from the source of electrons and move to the place which lacks electrons. Now look at this mechanism. This is an elimination reaction. We are going to learn about these type of reactions in chapter 7. By that time, you'll be able to draw such a mechanism yourself. For now, I want you to look at each step of this mechanism and identify which steps are proton transfer steps. So let me label each step, step 1, 2, and 3. Alright, so let's look at step 1. Is this a proton transfer step or not? Yes, it is. So the alcohol attack the hydronium ion, our acid, to take the proton, and then the bonding electron moves on oxygen to form these species. So this is a proton transfer step. Now look at step 2. Is this a proton transfer step? No, it isn't, because we don't have any base or acid reaction here, right? It is just loss of water. We are going to talk about that later. Now, how about step 3? Is this a proton transfer step? Yes, it is. So water will attack this molecule, takes the hydrogen, takes the proton, and the bonding electron forms the alkene for us. And water will be converted to hydronium ion, which is not drawn here. So this reaction will form hydronium ion. To draw the mechanism, the first step is to identify where the reactive electrons are. So in this example, let's add all the electrons, all the missing electrons to the molecules, label all the structures, and draw the mechanism. So let's start with putting the missing electrons. In the first structure, this structure, a benzene ring with OH attached to it, we call that phenol. So in phenol, we have divalent oxygen, and we know that divalent oxygen has 2 lone pairs of electrons. Then we have hydroxide ion in the next structure. So oxygen has a single bond to hydrogen. It's negatively charged. So monovalent oxygen, negatively charged, always has 3 pairs of electrons on it. Then we have phenoxide, similar to hydroxide. Again, oxygen is monovalent, negatively charged, So we have 3 pairs of electrons on it, and then water, divalent oxygen, has 2 pairs of electrons on it. So it should be pretty easy at this time in this course. Now let's label each structure. So if you look at here, phenol gets deprotonated, lost the proton, and converted to phenoxide. So phenol is our acid here, and phenoxide is our conjugate base. Now, hydroxide, except the proton, gets protonated and converted to water. So hydroxide is our base, and water is our conjugate acid. Now, to draw the arrow pushing mechanism. So we know that in acid and base reaction, the base always attacks the acid. So the lone pair on base attacks the proton on acid, and this bonding lone pair goes to the next atom, which is oxygen, to form the phenoxide and water. So this is how you can show the movement of electrons and draw the mechanism in this equation. Now, to determine the strength of acids and bases, we have 2 ways to consider. First one is looking at pKa values, which we call quantitative analysis, because we are using numbers and calculations. And second way is qualitative analysis. So there are a few rules that I'm gonna talk about later in this video to analyze acids and bases strengths and compare them with each other. In general chemistry, you calculated pKa values using these equations, as you can see them here. We are not gonna do calculations in this course. I don't want you to show any of that. But I want to show you where the pKa values, where these numbers are coming from. So when you have acid and base reaction, at equilibrium, you can calculate the equilibrium constant by dividing the concentration of the product over the concentration of the starting material to get this equation. If you have very diluted solution, the concentration of water is constant. So we can remove that from the equation, and then we get a new equation that can calculate Ka for us. The Ka values are different. We can have the values from a very small number, 10 to the negative 50th, to 10 to the 10 power, a very large number. So it's very hard to deal with these type of numbers. Therefore, chemists converted the Ka values to pKa values by taking negative log of Ka. What is nice about pKa is that we are looking at the numbers from negative 10 to 50. So they are much easier to compare. We can look at the table of pKa and compare the acidity and basicity of the compounds using these numbers. Here is the pKa values. This table is from your textbook, table 3.1. These numbers are very important. You need to use them for quantitative comparison of acids and bases. So when you look at this table, the lower the pKa value, the more negative the number gets. We have the stronger acid. So sulfuric acid has the lowest pKa value in this table, so it is the strongest acid in this table. Now, the higher the pKa values, the weaker the acid would get. So alkane has the highest number in this table, so it is the weakest acid in this table. We can also think in opposite way for bases. So if an alkane is a weak acid. In its basic form, it is the strongest base, and sulfuric acid, which is the strongest acid, in its basic form is going to be the weakest base. So each pKa unit represents an order of magnitude, meaning that if you compare an acids, like two acids with pKa of 10 and 16, acid with pKa of 10 is about 1 million times more acidic than the acid with pKa of 16. So just remember that these numbers represent the order of magnitude. Now, as a practice, look at these two structures, compare them using the pKa values, and decide which one is more acidic. So if you look at phenol, and you find phenol in this table, phenol has the pKa of 9.9, so the pKa for phenol is 9.9. And then if you look at this molecule, the functional group here is an alkene. So if you find an alkene in this paper is right here. The pKa value for that is 44. Now phenol has the lower pKa value, meaning that phenol is more acidic than alkene. So let's look at the structure of adrenaline molecule and determine which protons is the most basic protons in this structure. So the very first step is to determine the functional groups first. So if you look at here, this functional group, we have nitrogen attached to R2 group and hydrogen. This is an amine. This functional group is an alcohol. This one, OH attached to the benzene ring, it's phenol. And then the second step is to find the pKa values from the table. So the pKa for an amine is 38, alcohol is 16, and phenol is 9.9, approximately 10. So then here is the rule here. The higher the pKa value, the stronger the base would be. So meaning that amine, which has the highest value here, is our strongest base. Then we have an alcohol, and then we have phenol. Now if the question asks you which one is basically the most acidic proton, so we need to reverse this order. So for the acidic proton, phenol is the most acidic because it has the lower pKa value. So the lower the pKa value, the higher the acidity, or the stronger the acid would be. Using pKa values, we can also determine the direction of equilibrium. So the rule of thumb here is that equilibrium always favors formation of weaker acid, and weaker acid, we know that it always has higher pKa values. So the first step to determine the direction of equilibrium is to first find your acid and your conjugate acid in the equation. So if you look at here, this base react with water, deprotonate the water, so water is an acid here, and forms the conjugate acid of the base. So we know our acid and our conjugate acid. What we need to do is to use the pKa values and determine which one is the weaker acid. The pKa value for water is 15.7 and the pKa value for an alkane is 50. So we already know that. Now if you compare these two pKa, which one is higher? So obviously the alkane pKa is higher, meaning that alkane is the weaker acid. So the equilibrium favors formation of the weaker acid, meaning that the equilibrium prefers this direction. And the difference between these two pKa is high enough that even equilibrium can go one way completely. So this is the direction that is preferred. Now if you want to answer the question below, why is the equilibrium arrow is bigger on top, meaning that it favors the product, not the starting material. So the answer for that is equilibrium always prefers weaker acid. So this is a really important concept here. And the weaker acid always has higher pKa values.